Hi class, how are you today? Do you think I even care how you are today? Of course I do. I love you guys. The learning target for today is to be able to calculate probabilities of a binomial using a normal approximation. For the scale, you're 3 if you can calculate probabilities of a binomial using a normal approximation. You're 2 if you can convert R values to z-scores. You're 1 if you can convert R values to x values, and you're 0 if you cannot convert R values to x values. Let's get started. Section 6.6. Normal approximation to binomial distribution and to p-hat distribution. Focus points. State the assumptions needed to use the normal approximation to the binomial distribution. Compute mu and sigma for the normal approximation. Use the continuity correction to convert a range of R values to a corresponding range of normal x values. Convert the x values to a range of standardized z-scores and find the desired probabilities. And describe the sampling distribution for proportions p-hat. The probability that a new vaccine will protect adults from cholera is known to be 0.85. The vaccine is administered to 300 adults who must enter an area where the disease is prevalent. What is the probability that more than 280 of these adults will be protected from cholera by the vaccine? The question falls into the category of a binomial experiment, with the number of trials n equal to 300. The probability of success p equal to 0.85 and the number of successes r greater than 280. It is possible to use the formula for the binomial distribution to compute the probability that r is greater than 280. However, this approach would involve a number of tedious and long calculations. There is an easier way to do this problem. For under the conditions stated below, the normal distribution can be used to approximate the binomial distribution. Consider a binomial distribution where n is the number of trials, r is the number of successes, p is the probability of success on a single trial, and q is 1 minus p, the probability of failure on a single trial. So if np is greater than 5 and nq is greater than 5, then R has a binomial distribution that is approximated by a normal distribution, with mu as np and sigma is the square root of npq. Note, as n increases, the approximation becomes better, and therefore varies less, like we discovered in section 6.5. So we'll get back to that problem in a second, but one thing I want to talk about is let's look at some graphs. So graph the binomial distributions for which p is 0.25 and q is 0.75. And the number of trials is first n equals 3, then n equals 10, then n equals 25, and finally n equals 50. The authors used a computer program to obtain the binomial distributions for the given values of p, q, and n. The results have been organized and graphed in figures 634, 635, 636, and 637. So here are 3 of those graphs, and notice as n gets larger, it becomes more normal, much more of a bell-type curve. When n equals 3, the outline of the histogram does not even begin to take the shape of a normal curve. But when n equals 10, 25, or 50, it does begin to take a normal shape, indicated by the red curve. From a theoretical point of view, the histograms in those last 3 figures would have bars for all values of r from r equals 0 to r equals n. However, in the construction of these histograms, the bars of height less than 0.001 unit have been omitted, that is, in example, probabilities less than 0.001 have been rounded to 0. How to make a continuity correction. Convert the discrete random variable r, number of successes, to the continuous normal random variable x by doing the following. If r is the left point of an interval, subtract 0.5 to obtain the corresponding normal variable x, that is, x equals r minus 0.5. If r is a right point of an interval, add 0.5 to obtain the corresponding normal variable x, that is, x equals r plus 0.5. For instance, the probability that sits is less than or equal to r is less than or equal to 10, where r is a binomial random variable, is approximated by the probability that x is between 5.5 and 10.5, where x is the corresponding normal random variable, seen in this figure. So we just moved sits to 5.5 and 10 to 10.5. Remember, we did this back when we had frequency histograms. It's the same thing, because with a binomial you can only have whole number results. You can't have half a success. So to make things easy, we do the continuity correction to make it halfway. In this problem, n equals 300, r equals 280, p equals 0.85, and q equals 0.15. We're back to the original problem that we were working with. So 300 people, and we're looking for at least, or greater than, rather, 280 successes with a probability of 0.85 for a success and a probability of 0.15 for a failure. To determine if we can use a normal approximation of the binomial, we first need to find if NP is greater than 5 and NQ is greater than 5. So NP is 300 times 0.85, which is 255, and NQ is 300 times 0.15, which is 45. Since both NP and NQ are greater than 5, we can use a normal approximation of the binomial. So to find the probability that r is greater than 280, we must first convert r to an x value. Using the continuity correction, we convert the probability that r is greater than 280 into the probability that x is greater than 279.5. Then we convert the x value into a z-score. So back when we did z-scores, same thing. We're converting a raw score x into a z-score. So we use the formula x minus mu divided by sigma. Remember, mu is NP and sigma is the square root of NPQ. So we have 279.5 minus 300 times 0.85 divided by the square root of 300 times 0.85 times 0.15. So we get 279.5 minus 255 divided by the square root of 38.25. which gives us 24.5 divided by the square root of 38.25, which is approximately 3.96. So we go to our table that we've been calculating for normal distributions, and we find z is 3.96. And just like it said a few slides ago, anything that's less than 0.001 rounds to 0. So you'll also see in the table anything that is a z-score of 3.49 or greater approximates to 1. So what we do is the probability that z is greater than 3.96 is 1 minus the probability that it's less than or equal to 3.96. So the probability that it's less than or equal to 3.96 is 1. 1 minus 1 is 0. So, back to what the problem was talking about was a vaccine for cholera. Looks like it's essentially almost a 0% chance that the vaccine will help save 280 or more people, more than 280 people. So it's probably not a great vaccine. Sampling distributions for proportions. We have studied the sampling distribution for the mean. Now we have the tools to look at sampling distributions for proportions. Suppose we repeat a binomial experiment with n trials again and again, and for each n trials. Record the sample proportion of successes p hat equals r over n. The p hat values form a sampling distribution for proportions. Given that n is the number of binomial trials, fits constant, the n stays the same, r is the number of successes, p is the probability of success on each trial, q is 1 minus p, probability of failure on each trial. If np is greater than 5 and nq is greater than 5, then the random variable p hat equals r over n can be approximated by a normal random variable x with mean and standard deviation, with mean being p and standard deviation being the square root of pq divided by n. The annual crime rate in the Capitol Hill neighborhood of Denver is 111 victims per 1,000 residents. This means that 111 out of 1,000 residents have been victim of at least one crime. These crimes range from relatively minor crimes, stolen hubcaps or purse snatching, to major crimes like, murder. The Arms is an apartment building in this neighborhood that has 50 year-round residents. Suppose we view each of the n equals 50 residents as a binomial trial. The random variable r, which takes on values 0, 1, 2, all the way up to 50, which is n, represents the number of victims of at least one crime in the next year. What is the population probability p that a resident in the Capitol Hill neighborhood will be the victim of a crime next year? What is the probability q that a resident will not be a victim? Using the crime rate, we take p equals 111 divided by 1,000, which is 0.111, and q equals 1 minus p, which is 0.889. So consider the random variable p hat equals r over n, so r over 50. Can we approximate the distribution with a normal distribution? Explain. So np will give us 5.55 and nq will give us 44.45. Since they're both greater than 5, we can approximate the p hat distribution with a normal distribution. What are the mean and standard deviation for the p hat distribution? Well, the mean is p, 0.111. The standard deviation is the square root of pq over n, so 0.111 times 0.889 divided by 50, which is 0.044. And now time for the sponge. Number 1, let the number of successes r have a binomial distribution with n equals 200 and p equals 0.75. Use the normal distribution to approximate the probability that r is less than or equal to 160. And is the normal distribution a good approximation of the binomial distribution? And explain. And number 2, suppose we have a binomial experiment in which success is defined to be a particular quality or attribute that interests us. Suppose n is 33 and p is 0.21. Can we approximate the p hat distribution by a normal distribution? Why or why not? If so, what are the values of mu sub p hat and sigma sub p hat? That's it for the lesson. Once again, please make sure to take notes in the entire lesson, rank yourself, take a picture of everything, submit it all to Google Classroom, and have a good night.